This meeting is being recorded.
Got it.
You have to, screen shares disabled. Oh, host disabled.
Yes.
Screen shares disabled. Can you
Yep,
fix that?
I'm doing it right. Yep, got it.
I'm working on it. Oops, it went away. Where'd it go? Where did you go? So maybe I'll get it larger this way. Might like that better.
Your slideshow.
Slideshow. So it's showing okay?
Perfect, thank you.
Well, seems like a big leap here to try and talk about ecology and humanity, and ecology was easier than humanity. But it's interesting, we don't think much about ecology. So the definition is coming up on the next slide. It basically means the interrelationship of living things with one another and with the planet. And it considers these things I have listed here. So our living Earth needs energy, needs a flow of energy. We know about that. We don't think about it, but we know about it. And it's mostly the sun. The energy comes from the sun, but it's different. So the next thing on there is nutrient cycling, or could be element cycling. Could be other ways to phrase it, but it's an interesting difference from the energy, because the energy flows in on a daily basis and it stops flowing when the sun goes down and it's unavailable for the night, and then starts flowing again from, as I point out in one of the slides, from 93 million miles away, which is, not unimpressive. That's where our energy comes from. I mean, many of these things are marginally ludicrous, the actual reality of our planet and the universe. Well, there's no more nutrients arriving, and I find a lot of, when I really entertain the reality of ecology, it makes an impression on me. And so in terms of nutrient cycling, all the nutrients on the planet were delivered when the planet formed 4.5 billion years ago, and no more are arriving. There's been life on the planet for about 4 billion years, but there's no more nutrients. So all of the nutrients are constantly recycled, and they go into new life forms. And that is, I would say, foundational to ecology, that things flow from one organism to another. Ecosystem elaboration, that's the third thing on that list. Well, that's a nice picture of the Medha River. None of that used to exist. There was no life on the planet. There were none of those nice trees. The rivers weren't flowing. That's all emerged over time. All the life on the planet has emerged over time, and any given ecosystem and the planet itself has elaborated itself somehow over time into diverse life through competition, that's on the list, and symbiosis, and I make a point of that, in intense ways. The competition, I have a picture of a lion killing a zebra. Competition isn't everything eats everything else. I don't know if you've had breakfast yet, but if you did, you ate something that was formerly alive and is no longer alive and is now giving you life and has the energy of the sun in it. It's interesting stuff. It's not the kind of thing we think about from minute to minute, but it's very touching, the reality of our lives and our planet. And the last thing, it says emergent intelligence. And the slideshow kind of goes towards that in the end as we get into the human situation and certain absence of intelligence in terms of the problems that we have. But all things on the planet are emergent, including this intelligence, which we might characterize as flexible behavior, like this isn't working, maybe we should try something else. We haven't defined ecology, but it means in a relationship. So why might we be interested? Well, I would say all of us feel a certain separateness. We are all, and Einstein noted that in this way, taken out of a slightly longer quote, but that's the base of it. Everybody feels a little separate, probably not as separate as we think, being as our actually physical bodies are made out of molecules that used to be in other bodies, and the oxygen we breathe is made by other living organisms and pumped into the atmosphere. We're interrelated. So this is a quote by a Zen monk. It's from a film I have called Planetary, which is quite good. I think I had to pay a little bit to buy it and download it, but it was not much. But anyhow, she says, we're not on the earth, we are of the earth. We don't think about that very often, but are we just walking around on the planet? And if so, where did we come from? Did we land on, with parachutes from somewhere else? Where did we come from? Well, the actual fact of the matter is we evolved from the dynamics of the planet. The planet is our home. Planet is what makes our bodies. And so this, I give him his credit. He's a PhD geochemist, and he says the same thing. We're connected to the earth in every possible way. The easiest to see is every breath we take, because we're breathing for oxygen. We're breathing for oxygen to break down the hydrocarbon product of photosynthesis. The oxygen is pumped into the air by plants. The hydrocarbons were made by plants, and that gives us our life. And it complicates from there, but every part of our body is connected to the earth. So ecology is a great subject. The word was first used in 1886 by a biologist, Ernest Haeckel. So the literal translation is the study of the household. But let's see, a little broader definition is a study, and I put in and perceiving, but the study of interrelationships between living organisms with one another and with the planet. But I put in perceiving because it's not just study. We're embedded in this reality of interrelationship. And it was interesting. I looked it up again, probably last night. I've looked up the word many times, ecology, etymology. Where did the word come from? And it said it's from the Greek word oikos, and oikos could be defined as everything concerned with the landowner's life, including the family, the farmland, and his slaves. That was just, to me, an interesting reflection on the reality of life in Greece 2,000 years ago and where that word came from. So it includes ecology includes your house and your slaves. Oh, yes. So I have this nice diagram I got off the web some years ago. It shows the things that cycle, some of the things that cycle. The upper one that's blocked out on my screen, I think you can probably see it. It says lithosphere. That's the Earth's rocky structure, the crust, the mantle, and the core. But there are other ones on the left. It says cryosphere. That's ice. Well, ice cycles. We're all flipped out about ice melting, but that's what ice does. It's either forming or melting. That's what ice does. The biosphere, the sphere of life, down below. The hydrosphere, water cycle. Atmosphere cycles all the time. They left out a few things, so I added on the upper right. The sun is important to the ecology and cycles of the planet, and I added soil left. And we're going to briefly talk about these things. So here's the lithosphere, the actual physical structure of the Earth. It's a great little video that seems to be functioning properly. This is the dynamics of the Earth. I don't know. The center of the Earth is about 9,000 degrees. It's about the same temperature as the surface of the sun. The surface of the sun, center of the sun's a lot hotter. And then this heat from the core at 9,000 degrees, heat rises, pushes up through the mantle, both liquid rock and viscous plastic hits the surface, it hits the rocky crust and splits it apart. This is a nice picture of subduction of a plate, an ocean plate subducting under another plate because it's older and colder and heavier. That's why they subduct than the plate it hits. So it's actually denser and sinks. The point being the lithosphere cycles, and that itself is somewhat mind expanding because it looks so solid and it's not solid. So then I drew up this picture down below. This shows the age of the ocean crust on the planet. That's the flattened out planet sphere with the continents and the oceans. So the red is the youngest rock, and that goes down the center of the Atlantic and not quite the center of the Pacific and the other oceans. That's the youngest rock, and I can read that. It says 0 to 5 million years old. So this is where magma is pouring out, like in that picture that's present right now. Magma is pouring out in the mid-oceanic rifts. It pushes to the east and the west. It cools. It gets heavier. And it continues to push east and west until it reaches continents. Continents are made out of a different kind of rock, lighter rock. You could argue they're made out of glass because they're high silica rock. And the heavy crust sinks underneath. So the point here is there's no, planet's 4.5 billion years old, but there's no ocean crust that's older than 200 million years, 200 million years. Because it cycles. Who would think that the solid crust of the Earth cycles? But it's reflective of the astonishing dynamics of the planet. The atmosphere cycles. So this graph chart shows the gases of the atmosphere. I circled them so you can see them. So the atmosphere is 78% nitrogen. I circled that. Up above, that says carbon dioxide. I actually corrected it because it says 350 parts per million. I just got a percentage there, but that's 350, and it's changed since this chart was made. It's now 420 parts per million. You know, that's not a lot of carbon dioxide. We're concerned about it, but remember, it's parts per million, whereas the other percentages, the atmosphere is mostly nitrogen and oxygen. There's oxygen, 21% oxygen. The nitrogen and the oxygen are totally a product. Nitrogen is released by nitrogen, forget the term, it's not nitrogen fixing, it's nitrogen releasing bacteria that break down organic matter and release the nitrogen into the atmosphere as an inert molecule, N2, which fills their electron shells. We talked about electron shells several weeks ago, and it's really so simple and so fascinating and so easy to understand. But elements like to have their electron shells full, and then if they do, they're inert and they don't react with anything. So the atmosphere is 78% nitrogen, but it's unavailable to life. Why? Because it's inert. It won't react. And only nitrogen-fixing bacteria, it's the only living organisms on the planet that can make nitrogen available for life. And life cannot exist without nitrogen. It doesn't need a large percentage, like probably less than 1%. I mean, our bodies are probably less than 1% nitrogen, but we have no bodies that are for nitrogen. So oxygen. Totally very reactive. We've talked about it. It exists in the atmosphere as O2. I forget if the electron shells are full, but or not. But it's a very reactive element. It likes to react with other things, and that's the value. It's both the danger and the value of oxygen. But that's why we breathe. It's taking oxygen, breaks apart the product of photosynthesis, and makes the energy of the sun available. So we can wave our hands around. You know, that's what gives us the energy for life. It's the energy of the sun. I mean, I thought about that the other day as I was going through this. That wow, we are actually little stars. Our energy is coming from the energy of the sun. That's the only reason we're alive. So what else here? So this is the atmosphere over time. And let's see, I think maybe, yeah, I circled the 4 at the bottom there just to show that's billions of years. So 4 billion years ago, 3, 2, 1. That's how the atmosphere has changed over time. The biosphere has completely altered the chemistry of the atmosphere. It's pumped the carbon dioxide out of the atmosphere. So now it's only 400 parts per million. And it has pumped oxygen into the atmosphere. Oxygen is reactive. It would not be there. I looked it up last night because Google knows everything. Oxygen would last about 5,000 years without photosynthesis. And then there would be zero oxygen. And every oxygen breathing organism would expire. But photosynthesis is widespread, millions of tons of photosynthetic organisms, and so the oxygen stays at 21%. And by the way, we might have seen this in a previous slideshow, but it went up to 30%. It's 21% now, it went up to 30% at a certain point in history when microbial organisms like bacteria and fungi, arguably microbial in that case, really didn't know how to break down the product of photosynthesis, especially lignin, wood. And so this structure, the carbon dioxide built up in the fossils in the ground, and oxygen was released and not being utilized by living organisms, and it built up 30%. Now, if the level of oxygen was 30% now, we would not be able to put out fires. I think of that when I build a fire every morning. What do I do to get it to burn? I blow on it. It makes a huge difference because you're getting more oxygen to those flames. So life created the atmosphere. So this is a reflection on the hydrosphere, the water sphere. What is the Earth is 75% covered by oceans, water, but life is implicated in the cycling of water on the planet because, especially the tropical rainforests, they send at least 30% of the rain that falls on them is evaporated back into the atmosphere. So that's why one reason there's always clouds over rainforests is they're making their own rain. Water is constantly evaporating from the oceans and going into the atmosphere and cycling. So this is an interesting reflection on interrelationship. This is an interrelationship between the hydrosphere, water, and plate tectonics, which is the lithosphere. And it is thought when ocean plates are drawn down, subducted under continental plates, they're in the ocean. So they just automatically take a lot of water, goes down with the ocean plate. The water lowers the melting point of the rocks. It interacts chemically with the rocks and lowers the melting point. So it's easier for them to flow. And once this was realized, it's now thought that if it weren't for water subducting with these ocean plates, plate tectonics would come to an end, which means life would come to an end. These nutrients have to be recycled over long periods of time. All the nutrients necessary for life are constantly flowing to the ocean. They'd all be in the ocean, in ocean sediment, if it weren't for plate tectonics, which recycles them into various forms of lithospheric rocks, including granite. Granite forms underground. Granite is a high silica, which means, high quartz, high glass type of rock that is crystalline. Those crystals take ages, and the small crystals in granite, the quartz and the feldspar and the other crystals, take vastly long periods to form. And so the granite takes, I forget the actual number, but well over 1 million years. Probably has to cool over 20 million years deep underground, a mile underground, to form granite. But uplift and erosion raises it to the surface. So here we have Liberty Bell and early winter spires. This is rock that has been recycled through plate tectonics, but it's not available to life because it's in a solid form. We need something that will grind it up. What might that be? Well, the form of Liberty Bell and early winter spires, they have that dramatic, poetic shape because of the ice ages that have poured over Washington Pass. And I have here a graph of the ice ages, and I circled the color blue over on the lower left so that you could see that this is 1 million years ago. Here, my cursor, I think you can see that 2 million, 3 million at the bottom. These blue darts that are pointing downward are a series of ice ages over the last 2 million years, which is known as the Pleistocene Ice Age. 2.5 million years, it goes to right here, 2.5 million years. Look at how many glacial advances there have been on the planet over the last 2.5 million years. Well, that's what you need to grind up the product of plate tectonics and make those nutrients available to life. So somehow the planet functions in a way that makes it increasingly suitable to life. It's very mysterious. I've used the term Goldilocks effects. Science uses that term regularly, and it makes them a little nervous because everything is just so right for life not only to exist, but to flourish over time. There is a saying by a biologist, the guy who wrote The Eternal Frontier, Tim Flannery, great book about North America, Eternal Frontier. He said, if you want to know how good your soil is, if you want me to tell you how good your soil is, tell me when your last ice age was, because ice grinds up the rocks and makes the nutrients in the rocks available. But we've had plenty. We really don't want another one right now, not likely to get one, but there was a mile of ice in the Methow 15,000 years ago. Very stunning. And none of the life forms that we see were here. So I put an X here just to show the last ice age was one of the largest. They grew stronger over time, and we could easily have another one in the future, in spite of our concerns about carbon dioxide in the atmosphere. Things change over time. So then there's the soil, which is it can be known as this pedosphere. Pedo means soil. What's the soil made out of? Well, here we have water. It's made out of the hydrosphere. It's made out of the atmosphere. It's 25% air. It's made out of the biosphere, about 5% organic matter, and it's made out of the geosphere. That's what the soil is formed out of the other spheres. Without all those present, you don't have good soil, but with all those present, life flourishes in and on the soil. So that image left out the sun, I put it in, and this stunning facts about the sun. It's 93 million miles away. How is it, and it's 1 million times bigger than the Earth. How is it possible that something 93 million miles away is supplying the energy for the biosphere on the planet? Well, the way it's doing it is fusing 600 million tons. I've seen several different numbers. It doesn't really matter. I've seen 400 and 500. I don't think we know for sure. It's fusing enormous quantities of hydrogen into helium every second. There's a little bit of biomass, a little bit of mass of the hydrogen doesn't show up in the helium and is turned into energy. You can turn mass into energy. I don't know how to do it, but Einstein does. So of all that energy, that massive amount of energy from this burning star, only 1/1000th of the sun's energy reaches the Earth. 1% of that is captured by photosynthesis, and that drives the biosphere. Quite stunning. I mean, I like, there's this good fellow, Brian Swim. He's a big historian. He's a cosmologist. He has a PhD in gravity. He knows a lot of stuff. And when he says these things, he says, well, that's impressive. 600 million tons of hydrogen a second. Oh, well, that's impressive. These things are impressive. Somehow sometimes they don't move us in the way that they could. So photosynthesis, we don't think much about photosynthesis, but it is where all of the food on the planet comes from. It's a very complex process. Where did it come from? It wasn't here. It didn't used to exist. It evolved in bacteria. Bacteria somehow were taken into larger organisms that, if you remember, we call the larger organisms eukaryotes, larger cells with nucleus, and they now live inside of these eukaryotic plants as organelles, small organs called chloroplasts, and they are able to take the energy of the sun and use it to split hydrogen, which is electromagnetically attached to water quite firmly. They split the hydrogen away and they attach it to carbon dioxide, and you get the product sugar. The oxygen is released into the atmosphere. If we knew how to do this, if we could split hydrogen from oxygen, we would have an endless supply of energy, which would not be a good thing for the planet or for Homo sapiens. We're causing enough trouble with the energy that we have, but it is possible. And there's people debate a hydrogen economy. Yes, you can split hydrogen from oxygen, but they use natural gas, and it takes more energy to split the hydrogen than you get back when you recombine the hydrogen with oxygen in your possibly hydrogen car. There are a few cars that run hydrogen, but it's not easy to do. You need a very heavy duty tank. The hydrogen has to be compressed. It's highly explosive. I don't think it'll ever work, but the point is plants do it all the time. With the energy of the sun, the energy of a star 93 million miles away, is a trophic pyramid. Trophic means feeding, pyramid. So this shows the relative abundance of life forms on the planet and how the energy that is captured by photosynthesis is passed through the food chain. That's what this shows. It's measured in a form of energy called joules, and that's what the J is for. I remember looking it up some years ago. What is a joule? And it said it's about the energy of a mosquito flying into a wall. It's a very small measure of energy, but it's a measure of energy, and it could say watts, it could say other forms. But physicists like joules for some reason. So this shows that for every 1,000,000 joules of energy, sunlight reaching the Earth, only 1%, 10,000 joules, is captured by photosynthesis, captured by plants. So that means that energy is available to create sugar in the way we talked about. When a herbivore eats a plant, that energy has been captured by the plant. It's passed on to the herbivore, but only 10% of the energy is passed on to the herbivore. The rest escapes as heat. It's inefficient. Probably can't be improved. It's created quite a large biosphere on the planet, but that's the fact of the matter. Only 10% of the energy is passed on. Well, that reoccurs every time one organism eats another. So we have a secondary consumer. We have a carnivore, a mouse, eating that grasshopper. It only gets 10% of the energy that's present in the body of the grasshopper. And a larger creature eats the mouse. And I know I've shown this picture many times, and I just noticed this morning, it looks like that snake is eating a person. See that? In any case, there is a book called Why Large Fierce Animals Are Rare. And this is why. There's no energy at the top of the food chain. It's lost 90% every time it's passed along. There's just not that much food. It's all based on photosynthesis. It's all based on a star 93 million miles away. So this shows the biomass on the planet on a relative. It doesn't show quantity. There's about 600 million tons of biomass on the planet. If you look it up, that's what it says. Well, you can see at a glance what most of that biomass consists of: plants. Why? Because plants make their own food. They're autotrophs. That means they fill themselves. They feed themselves. Any photosynthetic organism makes its own food. So this includes also algae. And actually, we have down here at the bottom, there are some other organisms. Here's Protus. I'm running my cursor around it. I think you can see that. Well, we talked about diatoms, I think, last week or the week before. Diatoms are Protus. Diatoms are photosynthetic. Diatoms make, the claim was, and it holds up on Google anyhow, 25% of the oxygen in the atmosphere is from diatoms. They're photosynthetic. But look, why are there so few Protists then? And it's hard to explain why, but the trophic, the feeding pyramid in the ocean is upside down. There are more carnivores than there are herbivores. And maybe it's beyond the scope of this program to explain why, but it's an interesting phenomenon. The trophic food chain is upside down in the ocean, and that's why there's so few Protists. The answer is because they reproduce so quickly. They're just constantly reproducing, and so they're constantly being consumed and reappearing. I mean, reproducing. So, but down here's a few more things. Here's humans. Humans rate on this chart of biomass, but look at how much more. We've talked about this. Well, it shows up again in a more clearly, but look at livestock, humans, look at wild mammals. They're just about gone. There's almost as many worms, nematodes, as there are wild mammals. Anyhow, it's a problem. We talked a little bit about it. So these are the imperatives of the biological world. If the animals are thinking, I think they spend most of their time thinking about this. So this is the evolutionary journey here. This is a fish that evolved into an amphibian, that evolved into a reptile, that evolved into a primate. No, it's a true story. The evidence is compelling that this did occur. This is what they are required to do. And here's a little bit of evidence of, didn't quite end up where I thought, but where are you going to get your food? Well, if you're a heterotroph, autotroph, that means self-feeding. Heterotroph, other feeding. You're going to have to kill something and eat it. And that is the way the world works. And it is brutal. It is so brutal. It's brutal to human sensitivities. I don't think the lion's upset in the slightest. The zebras are probably pretty upset. But this happens, an uncountable number of times every day. Organisms kill other organisms and they eat them. But that's not the whole story, because the world is also symbiotic, which means life together. Life is symbiotic to a degree that is almost unfathomable. I am going to start a list, and I'll do an article in the Naturalist at some point on symbiosis, but it's pervasive. Symbiosis is pervasive on the planet, and this is just one example that I have here, that our cells have in them organelles. I mentioned this briefly earlier. Our cells are made up of organelles that evolve from bacteria. So the mitochondria, and I circled it here, our cells have innumerable mitochondria. I mean, I looked it up, 100 to 1 million in one cell. We have 5 trillion cells. These are bacterial in origin. Our mitochondria have their own DNA. That DNA does not reproduce with the DNA in the nucleus. It reproduces on its own. We get all of our mitochondrial DNA, our mitochondria, from our mother's genes. And it's well established that these were originally bacteria. So we have bacteria coexisting inside our cells as not only symbiotic, you just rest with that word, but they say it's a mutualism. They're mutually enhancing. The mitochondria has a place to live, probably gets some nutrients from the cell, and the mitochondria does its job, which is actually to break across those hydrocarbons and make the energy available to the cell and to the organism. It breaks down the hydrocarbons created by photosynthesis, then consumed by this organism. And chloroplasts. So I just circled a chloroplast in the upper picture there. So we don't have any chloroplasts, unfortunately, or we could be autotrophs and make our own candy bars. But all photosynthetic organisms have chloroplasts, and they're bacterial in origin, and they have their own DNA. So these are symbiosis, the very basis of at least our life, eukaryotic life, the larger celled life, multicellular organism is symbiotic at its foundation. So its life is both competitive and symbiotic to a degree that I think is unimaginable. And I think we can't quite grasp that that's the way this planet works. Cycling, we're talking about ecology. Everything, sun energy flows when the sun comes up, stops when the sun goes down. It powers the biosphere. The nutrients are not flowing in from outer space. They were all delivered 4.5 billion years ago. And they have to cycle or life would come to an end. So all these nutrients are necessary for life. I looked these things up. Plants are 45% carbon and 45% oxygen. That's 90%. They're almost completely carbon and oxygen plants. Our bodies are, what I saw was 18% carbon. Our bodies are less carbon, but high, lot of carbon. Carbon is the organic chemical. If you study organic chemistry, you study carbon chemistry. It is the quintessential element necessary for life. But we also cannot live without these other elements, phosphorus, nitrogen, oxygen. They have to cycle or they'd all be in ocean sediments and gone, but they do cycle. So we don't like the cycles very much, and this is one way they cycle. This is a dead deer being consumed by maggots. I remember that scene. I took that picture. I'll bet I took that picture 20 years ago, but it made I was mildly mortified. We don't like that part of the ecological story. But if you really entertain ecology, it definitely modifies the life and death journey, even for the individual, because we are part of something vastly larger than our concept of ourselves. And everything we are made of has been in other organisms and was initially formed in the center of stars. This is all true. It's all a big story. So one reason ecology is not popular, well, there's a bunch of dead things in the soil there because it's organic matter that gives the life to the soil. There's some skeletons in there, which is where skeletons ought to go instead of soaking them in formaldehyde and then putting them in a lead casket, which is what we do because we're so mortified by death. You could get into it, really. There's that strange statement by Walt Whitman. Something like death is better than anyone who dies is luckier than can be imagined. We don't know what he means, but it is a part of something real and huge. And we can get into it. So I put this little quote. I'm just going to pull it up here to try and soften the blow. First, musicians compose, and then they decompose because musicians cycle. Everything has to cycle. Everything donates the elements and nutrients in its body to the next generation of life. It's not a bad thing. So Krakatoa is a volcano in Indonesia, a very lively, active volcano. And I became interested in it a couple of years ago because it's now partially covered with the tropical rainforest. But Krakatoa blew up in 1883 completely. It blew up. it was heard. It was such a loud explosion. It was heard 4,000 miles away. It killed a lot of people, created tsunamis. The island disappeared. There's nothing left. It reappeared in 1927 because it's a volcano, and it reappeared out of the ocean. And now it re-exists as Anak Krakatoa, which means child of Krakatoa, because it reappeared, and it has a tropical rainforest on it. That's only 95 years after it reappeared out of the ocean. Well, that would be building an ecosystem. Scientists did go study it. And I have not recently seen the study, but our task here is to rebuild this ecosystem. How would it happen? So what do we need to build an ecosystem? Well, probably the first thing we're going to need is the sun. And this is, the list would be the order would be arbitrary, and I actually left something out of here. But let's see what we got. You need life. If you want to build an ecosystem, you need life. Where do you get life? We do not know the answer to that. The biologists and the ecologists would love to know how life formed on the planet. The evidence is it appeared one time, and that all organisms on the planet are related to the initial appearance of life. We don't know how it happened, but we do know that it evolved in complex forms, and over time, photosynthesis evolved, which is what we've talked about, using the energy of the sun to create food. Then, if you want abundant life, if you want a rainforest, you're going to have to start creating soil. So you're going to need some kind of organism that can break down the I forget the word. The volcanic rock is all you're going to have when a volcano appears out of the surface of the ocean. All you're going to have is volcanic rock. Some's got to break it down so plants can take root, and so that organic matter can start to collect. Well, lichens can live on bare rock. They don't need soil, and they produce chemicals that will slowly, very slowly, break down rocks. But lichens have all the time in the world. If it takes them 100,000 years to break down the rock they're living on, even a portion of the rock, they've got it. You need oxygen. Well, if you have photosynthesis, you'll have oxygen, but there was no oxygen in the original atmosphere. Well, if you want a rich ecosystem, you have to add animals. So you can cycle some of the plant material and have a more complex ecosystem. Where will they come from? They're a byproduct of photosynthesis. They eat the product of photosynthesis. And then you have an ecosystem that competes in the way that we talked about, eat, survive, reproduce. I think maybe this is my ecosystem. So this is not to be necessarily understood. This is a student's wonderful drawing of an ecosystem, and I put it up just for its complexity. It's so busy, you can't figure out what's going on. But what is going on here are the things we talked about. So I circled the sun up at the top there. Oh yes, we left out of our Krakatoa ecosystem water, but there's plenty of water. It's surrounded by the ocean. It's a tropical area. It's going to have plenty of rain. So precipitation, going to have some water flowing through. Plants appear, start making their own food. Soil is enriched by the existence of the plants, which need the soil. It's a symbiotic relationship. Over on the right, I circled CO2. Well, we think of CO2 as something undesirable, but that's the basis of food. The plants are making food out of carbon dioxide that exists at 400 parts per million. It's a good trick. You try and make food out of something that exists in 400 parts per million. In the atmosphere, it's a gas, oxygen. So then at the end, I circled an owl, just because you can't have animals until plants are creating food, an ecosystem, and then everything decomposes and flows back into itself. So we have the assignment, eat, survive, reproduce. What are some examples of eat, survive, reproduce? This is a bower, that little grassy structure in the middle of the picture, created by a bowerbird, which is a tropical bird. The male is interested in reproducing. It's a competitive process to acquire a mate who interprets your activity as adequate reflection of your genetic makeup, actually, to reproduce with you. So the bowerbird, to attract a female, improve its vitality, builds a bower, and that's the bower. But it not only builds a bower, but it needs to create these colorful background to attract female. And so it collects blue bottle caps and blue straws. And the female loves it and comes and goes. If she likes it all, she goes through the bower and they mate. And the next generation is created. Well, there's competition for reproduction there. And are we animals or are we not animals? So I put this in here. This is the same process. You know, humans are, the insight here is that humans are animals, and we think we're one step beyond, but we aren't much of a step. And this was not really, it wasn't realized, and when it was realized, it wasn't popular. So this really was initiated, this insight that humans are animals was initiated with Darwin's book in 1859, The Origin of Species, and that humans evolved from primates. And we are primates. Very unpopular, but we still considered ourselves on a pedestal above animals until E.O. Wilson, very famous biologist who died recently, a few months ago, wrote a book called Sociobiology, that the biology of humans is based on genetically programmed behavior. And that's what this is a picture of. You know, if you get a fast, hot car, you might be able to get a fast, hot chick. It's the same as a bowerbird, the exact same thing. So here we have this evolutionary process, eat, survive, reproduce, eat, survive. What comes next? Well, what came next was Homo sapiens. Is Homo sapiens different? We are animals. It's an emergent universe. The universe is constantly coming up with something new. Is Homo sapiens something new? Arguably, Homo sapiens is something new. Certainly, we have a big brain. And this is the evolution of the brain over time. This, the upper left, get my cursor here. This is a chimpanzee, 400 cubic centimeters. That's the size of their brain. It's not very big. They show some capacity to learn, some capacity for flexible behavior, but it's very limited. They are much more genetically a reflection of their genetically programmed behavior. This is Australopithecus, 450 cubic centimeters, Homo habilis, Homo erectus, Neanderthals, and our species. Our species, it says 1,300 cubic centimeters. What are you going to do with all that brain power? Well, what you see is what you get in terms of the planet that we live on. But the potential, the struggle seems to be for more flexible behavior, for something we call intelligence. So this is a Macapon Scott pebble. Was found in a cave in South Africa. I don't know when. In the 1900s sometime, but it was not native to that cave. It was not the same kind of rock. It was, so something put it there. It was a manuport, which means something transported by a living organism. I don't know if it's always humans, I cannot remember, but it means transported. It was found in 1925. It was carried there. It became realized that and the rocks type was from 20 miles away. It was realized it's 3 million years old. They were able to date it. There were no Homo genus at that time. We were just Australopithecines, pre-hominoid organisms. It must have been carried there by an Australopithecine and left in the cave. Why would it do that? Probably because he thought it looked like his wife. It's a bit of a joke, you know, they didn't marry at that time, but it has this human figure. It is considered in the anthropological circles the first evidence of symbolic thought. This is not a person. This is a rock that looks like a person. It's a symbol of a person. The creature that carried it was capable of using its brain to imagine that this was something other than what it was. Symbolic thought. Symbolic thought is big. Humans, I did drop how valuable is symbolic thought? Well, there's no good answer to that question. This is an interesting statement. And this is actually Krishnamurti said this, and it's so short and simple. I never forgot it. You know, I read it. I bet I read it 30 years ago in one of his books. You know, he was a philosopher, Krishnamurti. He said the word tree is not a tree. Well, give this a try. I mean, I did it this morning. I was thinking about this and looking out the window. There's a ponderosa pine tree out there. Well, ponderosa pine trees, you know, that tree is probably 100 years old. It takes 2 years for the cones to develop. It has these needles, what are so you start spouting all this information about this tree. It's all symbolic thought. I'm thinking about the tree. It's like a screen between me and the tree. That's what he's talking about. If you're thinking about the tree, you're not perceiving the tree in the way that you could in the absence of thought. Now, I'm not recommending that we stop thinking, but I am recommending that we take a break, because our brains are constantly creating, what do they call that? I forget, mind stream, it's just this constant stream of thinking. It's a screen between us and the actual physical world. And people like Krishnamurti would argue that there is an intensity to being on the planet that you will experience if you can experience the world without thinking about it. So this is the General Sherman tree. I love that picture. I love that tree. It's the largest single organism on the planet. So has thinking replaced reality? Well, it's not just Krishnamurti. He might sound like a Indian weirdo. So I found this quote by Yuval Harari in the book Sapiens, which is a brief history of humankind, which is a very popular book and read by probably most of you. And he says, ever since the cognitive revolutions, sapiens, that would be us, has been living in a dual reality. On the one hand, the objective reality of rivers, trees, lions, also known as the earth, the planet. And on the other hand, the imagined reality of gods, nations, and corporations. Those are all imaginary. Those are all created by thought. There would be no gods without thought. You need a story. As time went by, the imagined reality became ever more powerful, so that today the very survival of rivers, trees, and lions depends on the grace of imagined entities such as the United States and Google. I don't know what degree you agree with that. I can put it that way. But often when I say the United States, I say the so-called United States. It's just an idea shared by, it's a meme shared by 350 million people who live on this continent. So this is an interesting reflection on the evolution and power of symbolic thought. These are the number of chops, and I think I circled the first one up top there. The number of strikes it took over time, developed over time to create tools. Many of these are weapons. The first one, I don't know, it's a chopper. So you're probably not going to kill anything with it, but that took about 17 strikes. Well, to start out with a rock and create a chopper that you're going to hit 17 times, you need some concept in your brain that you're going to hit this a number of times and change the shape of it. You are engaging in symbolic thought. Symbolic thought has evolved over time, so that this was probably an Australopithecine with a chopper. This is a hand axe. It says hand axe, it's a Homo erectus, they were on the planet a million years ago. Our species is 200,000 years old. I forget the exact numbers for Homo erectus. They actually coexisted with Homo sapiens. It's thought Homo sapiens probably killed them. In any case, Homo erectus, early human, smaller brain capacity, would have been around 1,000 cubic centimeters instead of 1,800. It created these hand axes that much more finely shaped than this pebble chopper. You had to plan ahead, 35 chops. Look at it increase here, 65. Later Homo erectus, Neanderthals, 111. Cro-Magnon, which is Homo sapiens in Europe, they made these very refined blades that took up to 250. You had to plan ahead. You had to live in your head and have the capacity for symbolic thought. It's been very powerful. It's just good to be aware of it, that we are doing this. I pulled up a nuclear bomb. Where did that come from? It came from the capacity to imagine the world, manipulate the materials in the world, and create this more refined weapon, actually, that we can only hope is never used again. This is an essay by Jared Diamond. That's the title, The Worst Mistake in the History of the Human Race. Do you know what he's talking about? That essay, Jared Diamond is a very famous anthropologist from California. He wrote Guns, Germs, and Steel, which everybody's heard of. He says the worst mistake we ever made was agriculture. Really, I'm just pointing out here that this is part of the evolutionary story of humanity. I just read this book called Nissa. That's the cover. She's a Kung San native in the Kalahari Desert in Africa, hunter-gatherer. The book was written in 1980. The anthropologist was there in the 70s, so it's dated. But she was there with him for almost 2 years. I highly respect this woman who wrote this book because she lived with the Kung San for almost 2 years. It's a great book. It's got a lot of interesting, fascinating dynamics of how they live with one another. But one thing that really struck me was Nissa says at a certain point, anytime she found anything alive, she killed it and ate it. She might bring it back. She'd probably bring it back to the village. I mean, it might be a turtle, it might be a lizard, it might be a bird. If it's an edible root, she'll dig it up. If it's a bigger animal, she'll go get the hunters and they'll stab it with these blades that they were able to make and bring it back and distribute it to the community. They killed everything that they could. They were always hungry. And what did that give rise to? It gave rise to the worst mistake in the history of humanity, agriculture. This is a great big history type image. Big history is big on this story that agriculture arose in these yellow places on the map. Agriculture arose independently. This has 5 different centers. These places were not in touch with one another, arguably. I mean, if there's any argument, it was that in the United States, agriculture was carried there from central Mexico. In fact, I guess it almost had to be because they were growing corn, which came from central Mexico. But the other ones, agriculture arose independently in these centers of urban civilization around the planet in a very similar time period. I think it would have been between 5,000 and 10,000 years ago. It was a natural outgrowth of the growth of the human population and the diminishing amount of wildlife. They were hungry. They noticed that they brought the plants back to the village to process the plants and eat them, and the seeds would germinate the next spring. And that's how people became aware of agriculture. So I guess I'm saying this is an interesting emergent property of Homo sapiens, but also taking issue a bit with Jared Diamond. And I don't know if he's categorical about that. He's just making the point that this led to the problems we have today. These are some of the 75 large mammals that lived on the North American continent 15,000 years ago. And by 10,000 years ago, they were all extinct. What happened to them? The newly arrived Homo sapiens killed them and ate them. That's what happened to them. I mean, they didn't kill the saber-toothed tigers, but they killed the prey of the saber-toothed tigers, and the saber-toothed tigers went extinct. So these fossils are all over North America. All these creatures were here. We had 5 species of elephants. There were more elephants and more large herbivores in North America than there were in Africa. There are pictures of these huge herds in Africa. The real Serengeti was in the North America, but it's gone. And it's because of Homo sapiens. So Homo sapiens is a powerful force. We know that. Homo sapiens, Homo sapiens is an animal. Animals are concerned about eat, survive, reproduce. I mean, I'll give them, if they are concerned about anything else, that's fine with me. I'm not accusing them of that, but I think those are the main concerns. Humans are animals. We are concerned about eating. In fact, I haven't had breakfast. Surviving and reproducing. The point here is we're self-centered. All animals are self-centered. It has to start. Any kind of consciousness has to start in the living organism, in the brain of the living organism. It's a natural phenomenon. It may not be the final emergent possibility of Homo sapiens. So this is a picture of what we thought the universe looked like, until at the moment. I cannot remember when that shifted. I do remember that we've only realized that the Milky Way was not the only galaxy in the planet in 1927, less than 100 years ago. We are now think there's at least 2 trillion galaxies in the universe. We didn't even know the Milky Way was a galaxy. And then we thought it was the only galaxy until 1927, when Hubble had a bigger telescope and could see out and see a few other galaxies. So even our insight into the universe is emergent. And so when people suggested that the Earth might not be the center of the universe, they were killed. And this is a guy, Bernard Palissy, who was burned at the stake in 1603 because he said that the Earth is not the center of the universe. It's a reflection on the fact that biologically, genetically, we think we are the center of the universe. That's how we experience the universe, from the center, from our brain. But it turns out, that's the beauty of ecology. It informs us, oh, we're not the center. We're connected to all living things. The church indulgences. So this is a reflection on the symbolic power of the mind to create bullshit. I have a good book. It's called Radical Honesty. And his main point in the book is the mind is a bullshit machine. It just cranks out bullshit. And you have to be aware of the power of the mind. So the whole culture goes along with this bullshit. So these were indulgences sold by the Catholic Church. And depending on how much money you had, you could buy your way into heaven. And it was expensive for rich people and very cheap for poor people. I looked it up. How much was a florin? It says poor people only had to pay 1/4 of a florin. That was about a penny. So it was a good deal. If you were poor, you could get into heaven it's just bullshit, just complete bullshit. The witch hunts. The witch hunts went on for 300 years. Who were the witches? The witches were the women who either lived singly, were herbalists, knew how to use plants, which was considered sorcery, or they were birthers. They knew how to give birth to people, and it was considered sorcery. And I think it threatened the men. I think that was a thing. It threatened the earth-centered view, the self-centered view of the men, and they killed them. They killed 1 million women over 300 years. It's just more bullshit. So this is some current bullshit. Here's a picture I just saw a couple of days ago, and I took it off the web. This is a suburb of Dubai. The population of Dubai, I think I wrote it down. I think it's 3 million people. There's no water in Dubai, and they don't grow any food in Dubai. They created this artificial environment because they can. Where do they get their water? They get it from desalination, 99% desalination. It's 100% fossil fuel. From the sun that was stored in fossils to create their water. It's a totally non-ecological, totally unsustainable, but people are ecology blind, so they think it's fine. It's a limitation of the human mind. Yes, the limitations of the human mind. So we're going to take a look here at the limitations of the human mind. And so this is a little game. It's very easy to play. You just need to read the card to yourself. This guy's holding a card, and you're supposed to read it and see what it says. So the point of this card is most people, I would say 95% of the people who read it think it says, you will pick the red card. But that's not what it says. What it does say is you will pick the red card. There's 2 thes. Most people do not see them. I can't communicate with you, so I don't know how this worked for you. But the point is, the ultimate arbiter of what we are conscious of is the brain. The brain filters and feeds to us through our consciousness what it thinks we need to know. We have no use for 2 thes, so it just blots it out, and we can't see it. And I've shown this in public, and you have to go up to the screen and point out the second the, or people don't see it. So there's a saying that characterizes this, and that is that we don't see the world as it is. We see the world as we are. Now, I'm claiming that this is a fact, and you may or may not agree. It's not, I don't think you would probably disagree that we have some, but the point is to be aware of it. The point is the awareness that we are not seeing the world 100% clearly is a step towards intelligence. So I wanted to show this something by Piaget, and I don't have time. I've downloaded these short films. So I looked up, couldn't find the ones I have downloaded because I downloaded them 10 years ago. But there's this one called, if you type this into YouTube, a typical child on Piaget's conservation tasks. This particular one, 4 minutes long, showed what I would want to show. It just shows that any humans, in this case, very young humans, 3 years old, their understanding of the world grows with time. And they do these little experiments with children. There's one where they have 2 glasses of water, and they have exactly the same amount of water. And he says, and the teacher asks this young child to 3, 4 years old, which glass has, do they have the same amount of water, or does one half glass have more than the other one? And the child, they look the same, they are the same, child says they're the same. And then the teacher pours one of the glasses into a skinnier, taller glass, so it's taller. And the teacher says, now which glass has more water, or are they the same? And the child always says, probably always, if it's young enough, the glass that's taller has more water because it looks like more water. The point being, everything we know about the earth, we learn over time. And you can see it in these young students, these young children. So it's very delightful to watch these Piaget experiments. And it brings home the fact intelligence is an emergent phenomenon. And that would be my ultimate point. Intelligence is an emergent phenomenon. It's an emergent universe. So we're towards the end here. This is oil production in the United States over time. And the point of this graph is the depletion rate of petroleum in the United States is increasing rapidly because all the big wells were drilled 40 and 50 and 30 years ago. They're gone. And now we're into sucking oil out of rocks. Fracked wells only last about 3 years. And they deplete 50% in the first year. And it's a toxic process. They use chemicals that they're pumping into the oil is a finite source of energy. That is the ultimate point. The planet is finite, and petroleum, fossil fuels are a product of photosynthesis that has been stored in the crust of the earth. It's a finite resource. It will run out someday, but we're energy blind. It's a growth potential for humanity to grow into intelligence, to understand how energy works on the planet, and that our energy foundation right now is very finite and is depleting. This is a graph that shows wildlife on, I think vertebrate wildlife or mammals on the planet, wild animals compared to the biomass of livestock and humans. You may have seen this before, but the biomass on the planet for mammals is now 96% cows, livestock actually, and humans, and 4% wildlife. So we don't really see this happening, but we are impoverishing the planet. We're impoverishing the biodiversity of the planet. Well, eat, survive, reproduce, that's its natural drive. The question is more possible? The answer is yes. Intelligence is an emergent property of the universe. So I can see Lisa, she's the only person I can see, but you remember Scott used to have a t-shirt. It said, insanity is inherited. You get it from your children. Well, intelligence is inherited, and you get it from your parents, actually, and you get it from your community. And, humanity is working on it. And to me, forget where I go with this. What's it all about? It's all about ecology. It's all about interrelationship. And we're waking up to the fact humanity created this word, ecology, 100 years ago, 150 years ago. All these insights into these cycles, all created by the power of the human mind to understand the world it lives in. It's an emergent universe. This shows some of the qualities of emergence. In the early universe, there was just hydrogen and helium. That's what we are told. And science thinks that's true, and it probably is true. All the evidence points to a very simple Earth. The universe has emerged over time. There were no galaxies. There were no stars. Stars are a product of hydrogen being pulled into a dense mass by gravity. And there's so much hydrogen, and it's compacted so tightly that it ignites, and it creates stars. This is the sun. Our sun is a star. All the elements on the periodic table, this is the periodic table, they did not formerly exist. They emerged from the dynamic activities of the universe. They're created in stars and in supernova explosions. You can't have rocky planets without the elements. So planets are a product of the emergent power of the universe. This is the emergence of life. This is what the first life looked like, bacteria. There was no life. It emerged from the properties, the inherent properties of the elements, that they attract one another, that they want their electron shells full, and they combine with one another and create new unexpected properties, including life. This is photosynthesis. This is a eukaryotic cell. They did not, the first cells were all prokaryotic. They were tiny, they had no nucleus. They didn't tend to form multicellular organisms. This has evolved over time. Now we have trees. So that fly is not supposed to be there. Oh, he came up. So this is art from the caves in Europe. And I love the art, and it's a symbolic representation of the animals they ate. And I love it, and it's beautiful, but I think possibly more important is insight. So I put this fly up here. You know, what's happening with humanity is we're gaining insight into our lives and into the planet we live on, and the interrelationships. We're towards the end here. This is just a little cartoon. Why your dog is happier than you are. The dog and the guy are approaching a park. The dog sees the park. The guy's head is full of symbolic activity. The guy is thinking about his problems and how things aren't going right, and they just need to be different. And the dog isn't doing that. The dog sees what's in front of it. So I recommend go out and look at a tree and don't think about the tree. You don't have to spend the whole day doing that. Just give it a shot. So this is the last slide. It's funny, it actually evokes emotion in me, which I'm going to suppress because I put this up here and it didn't do this when I put it up, but you see the beauty of life. You see the beauty of humanity, and the potential for humanity blows me away. The potential for humanity to live well on the planet exists. It could be an emergent property of the universe. I think we're working towards it. So now I'm drawing up a sort of out there quote. It happens to be my most famous quote of all time. I got this quote I worked on a Mennonite farm in Pennsylvania when I was 18, and they had a book on the shelf called Protestant Mystics. And I'm not a Protestant, I'm not a Christian, and I'm not a mystic. But this quote this is only a part of it because I couldn't fit it all on here. And here it is. So this woman had this experience. She was sitting on the porch, and she says, gray days, because a lot of our days are gray. We feel, a little down. There's this weight, like that guy in the picture with the dog. And everything shifted. And all of a sudden, she said she looked into the heart of reality, and it was ravishingly, ecstatically beautiful and filled to the overflowing with a wild joy. I don't know how often any of us experience wild joy, but it is an emergent property of the universe, and it's possible. We are not on the earth, we are of the earth. This is our home. This is the earth household. So that's our 1 hour journey through ecology. Muchas gracias. Que le vaya bien. If you want to argue with me, there's my email.
What a beautiful presentation. I love that last slide. It was so hopeful and joyful. Thank you.
The children?
Yeah.
I wanted to cry. I couldn't believe it. I'm so glad that I am capable of that kind of emotional reaction.
So great.
I guess I'm not screen sharing. I'm stopping.